I'm going to record because I always forget to do that. So just talking about what's on the agenda and making sure that everybody's seeing that. You've got you're going to have one little problem from the 4.1 classwork to work on and finish up and send to me just by email by Friday, sometime on Friday. You'll have an investigation to work on with your group mates, and that'll be due by the end of the day on Saturday. And then, of course, you've got the videos to watch, the notes to fill in for 4.1, 4.2, and 4.3. We're going to do 4.1 or most of it today, and you'll get the hang of it pretty quickly. It's going to feel like a little bit of a breath of fresh air by the time we get going in chapter 4. Speaking of which, let's go ahead and start taking a look at chapter 4. So I need to get my document cam front and center here. Let me share my screen. And so chapter 4 is all about what happens when we have a harmonic oscillator that is, maybe it's damped, maybe it's not. That's not the important thing. But what if it's not the only game in town? What if it's not the only thing that's happening? What if there's more than just damping going on with the harmonic oscillator? So up to this point, you guys can all see my my document camera screen, right? That's okay, showing up. Okay. So up to this point, we've really seen two types of harmonic motion. The first type was the one that we ran into first way back in chapter 2, which was free harmonic motion. That's really just a fancy way of saying undamped. And this has another name, simple harmonic motion or oscillation. Oscillation is the word that you use when you want to sound smart, right? Simple harmonic motion, that works. If you use the word oscillation, then you sound even extra smart. And so basically this is just saying, set it into motion, and it just goes forever. So there's no damping. Right? It's technically pretty boring and also pretty much unlike the real world, because in the real world, there's always damping. Even if you have the simplest molecular spring, and yeah, there are things called molecular springs, which are basically, they're polymers that when you stretch them, they want to pull back to the same shape. And so these lovely little polymers you can stretch and then they pull back, and even they have damping as a result of the bonding energy not being completely conserved. Some of it gets given off as basically waste heat. So free, true, simple harmonic motion, simple harmonic oscillation doesn't actually work in the real world. It doesn't exist in the real world. You're always going to have some decay due to damping. But this is really useful for us as a kind of a first step in the modeling of harmonic motion. So the second type that we dealt with was what we would call damped harmonic oscillation. And I'm just going to abbreviate with H and O because I don't want to write all that stuff. And that was when we introduced the dy dt term in the differential equation, remember? So before, up here, undamped means that the B term or the Y prime term is equal to 0. But for a damped harmonic oscillator, we're basically saying, okay, so we're going to introduce some kind of resistance to velocity, not necessarily to not necessarily to position, but how quickly that position is changing. So the faster the oscillator is moving, the more damping it's going to experience. The slower it moves, the less damping it experiences, right? And this is kind of our stereotypical example for this is always the shock absorber, right? The stiffer the spring, the more liquid, the more gooey liquid is in the dash pot, the more this thing is going to resist motion. And so when you go over a bump, a stiffer spring is going to resist motion more, right? So this is caused by friction, and it opposes motion. So technically it opposes velocity, right? Not position. That's the spring constant. The spring constant says, stretch it further, I pull harder. That's not the way this works. This says, move faster, and I resist more, right? The fancy name for this is it's caused by, it's created by what's called a dash pot. It's an old-timey word for what you and I might think of as a shock absorber, something that usually contains a fluid that is a significant amount of resistance, viscosity, the fancy word for it, and this dash pot counteracts velocity.
Is that because fluids are compressible?
That's part of it, although you can also get partially compressible fluid. So for example, air is partially compressible, but it can work, and gases can work just fine in a dash pot. So it's really just the fact that there's more particles, there's more stuff that the spring is actually coming into contact with. At the molecular level, you're basically making a whole bunch more collisions that the spring has to deal with, rather than just be moving the mass from one place to another. Right? But we don't get too far into the weeds on modeling molecular wiggling. By the way, you can do a really nice job of modeling the forces the forces that cause bonding, like chemical bonding. You can model them with springs, and you can use this same technique, the type of math that we're doing, to basically come up with how much energy would we expect to have to put in to see vibration for a molecule, vibrational energy. And it works out pretty well. I mean, the math it misses a couple of the kind of real world features of what's going on. But a simple ball and spring model for molecules actually is really, really good as a first order approximation of what's going on. So it's worth noting that in both of these cases, neither accounts for forces outside the harmonic oscillator. In other words, if you walk into the room and you see this harmonic oscillator wobbling on the table, and you walk up and you go, huh, that's really weird, and you breathe on it and you cause it to move because of you breathing on the oscillator, you've just introduced an outside force that's not the spring, and it's not friction with the table or something. It's this external thing, this outside force. So they only model the oscillator. They don't model anything outside the oscillator. But it's not very helpful in the real world. We want to be able to see how oscillators interact with things. We want to be able to walk up and poke something and see what happens. So we're going to add another external force that's only dependent upon time. And this is important because remember, time, that's our independent variable. So we're talking about introducing another force that's also dependent on time, but it's not dependent on the other variables involved. So it's not dependent upon position, has nothing to do with velocity. It's only dependent upon time. So we're talking about an equation that's going to look something like this. If you remember, our general form of our differential equation was mass times y double prime plus b times y prime plus k times y equals, and it used to be equal to 0, but now what we're going to do is say that's equal to some force, outside force, f of t. And so just a reminder, this of course was the mass. That's what we would call acceleration. Acceleration. This b is what we call the damping coefficient. Y prime has a name, we call that velocity. K, that's the spring. And y is the position. And this guy over here, this is the time-dependent external force. So maybe it's your kid brother walking up and poking the spring every second to annoy you. Maybe it's there's a fan blowing and it creates just a constant breeze blowing on your harmonic oscillator, right? It's external, but it's time dependent, right? But it's not dependent upon anything else going on inside the oscillator. So what we're going to do is, just like we did before, we're going to manipulate this thing. We're going to adjust it, move it around to make it a little bit easier for us to read and make sense of. So we can rewrite this thing as by dividing out some stuff, y double prime plus b over m times y prime plus k over m times y is equal to 1 over m times this function f of t. Now, 1 over m times the function f of t. Remember, mass is just a parameter. It's just a number. So this is just a number times that function. So sometimes this is also written as a new function named g of t. Doesn't matter, right? Doesn't matter. And just like we did in previous sections, we said this b over m, if I don't want to drag around the b and the m, I can simplify this and just write it as y double prime plus p times y prime plus q times y. And so this sometimes you'll see as the general form, but it's really the exact same thing as the line previous. It's just a shorthand way of saying it, right? So however we decide to write it, it's a second order differential equation on the left-hand side, but on the right-hand side, there's something else. It's not just equal to 0. There's something else going on. And because the entire equation is not just terms of y and its derivative, right, like it is over here, this side has nothing to do with y or its derivative. So suddenly we're dealing with a situation that is non-homogeneous. There's a word we haven't heard in a while. Non-homogeneous. If you remember way back to chapter 1, a homogeneous differential equation was one that only had terms having to do with y or y prime, the dependent variable or its derivatives, right? So here's an example of a non-homogeneous one because it's no longer 0 on the right-hand side. But how the hell are we going to solve that? We can't turn this into some kind of a first-order system because what the heck am I going to do with that? If only it were 0, then I'd be able to just ignore it and use the methods that I already know. And no big surprise, that's pretty much exactly what we're going to do. And so when we take a look on the next page, we have the extended version of that linearity principle that we saw ages and ages ago for the first time. The extended linearity principle says, let's say you've got a non-homogeneous equation of this form. Now, right here, you recognize this part of it. That part of it is what we would call the homogeneous part. This is a variation of the chapter 1 theorem that has to do with second order differential equations. Now, this guy right here, that's the homogeneous part. Over here, this is what makes it non-homogeneous. So all of this stuff right here, that's the homogeneous differential equation, right? So if we just ignore the g of t, if we ignore that function and say, I'm just going to treat it like it was a 3.6 problem, right? I know how to solve those. You can do that. You will solve the homogeneous part of the solution. You'll get y sub h. And guess what? Just like we did way back in chapter 1, if you can find y sub h and a particular solution, and you add them together, you get your general solution. So this is what we're shooting for in this section. You want the general solution that is equal to your homogeneous part of the solution plus your particular. This we know how to find from chapters 2 and 3, right? Actually, chapter 3, to be honest. This one, it's going to take a little bit more work. This is really where chapter 4 steps in. We're going to figure out how to solve and get a particular solution if we start off knowing this thing right there. So in the end, if this thing right there, the homogeneous part, is all of this stuff right there, that's all of that, then all we have to do is figure out what that particular solution is, and we're home free. So at the bottom of the page, you'll see, first step, we find the general solution for the associated unforced differential equation, the homogeneous part. Step 2, find any one particular solution. Step 3, add them together. And you're done. It's that easy. Of course, just like we saw at the end of chapter 1, how do we do that? How do we do that step 2? I got step 1. We're experts in that after chapter 3. But how do we do step 2? And that's what we're going to be focusing on on this for the next, 2 sections in 4.1 and 4.2. So let's consider the case where there's damping. So sorry, I got to straighten out my papers. I don't need all that stuff underneath there. So I got papers all over the place here. So let's consider the case where there's damping. We have damping over a long time. What's going to happen to our homogeneous system? Now, homogeneous means not forced, right? So what's going to happen to our unforced system over a very long time? This is code language for as t approaches infinity. What do you think? It's an unforced harmonic oscillator with damping. What's going to happen to it if I wait long enough?
It goes towards 0?
Yeah, it stops, right? It heads towards equilibrium. So no big shakes there. We know that if we play the clock forward and you wait long enough, no matter what your initial conditions are, this thing's going to stop. Or should I say, it'll approach equilibrium. So we can say, without any loss of generality, that all y sub h parts of the solution head towards 0. And the reason for that, of course, is because there's damping. My dumb dog. Right? If you wait long enough, the thing will stop. So the fancier mathematical way you could write this would be y sub h tends towards 0 as t tends towards infinity. But it's worth noting, apparently we have a package at the front door, and my dog does not like the UPS driver. So y sub h tends towards 0 as t approaches infinity, but y sub p doesn't necessarily. Right? So if you have a forcing function that's poking, it just keeps going forever, then yeah, your homogeneous part of the solution is just going to fade away. But the poking part, that's the particular part, is going to kind of kick in. So what about the forced system with damping? Well, after a long time, we can say that only the particular part of the solution matters to the overall solution. Of a forced, damped harmonic oscillator. And there's language that gets used around this that sometimes it seems a little strange, but it makes sense if you consider the fact that it's language that's been around for 100+ years, and so it sounds a little old-fashioned. But the old-fashioned language is they will sometimes refer to the natural response. and the steady state response. The natural response is what you know of as the y sub h. And this is all from the structure of the oscillator. Right? So everything about the natural response comes from the oscillator itself. So if you want to know if it's a mass on a spring, you want to know what y sub h is, you're going to have to look at the spring. You're going to have to look at what damping there is going on with the oscillator, whether there's any friction going on, and you're going to have to look at how much mass is on the spring. But it's all kind of self-contained. So the natural response is literally, naturally, how does this thing behave? In the absence of anything else external, how does this thing behave? That's the natural response. The steady state response, however, that's the y sub p part of this. And that's all coming from the effects of the forcing function. On the harmonic oscillator. So you can have a forcing function that will cause this particular oscillator to behave this way in the long run. But if you apply that same force to a different oscillator, you might get a different y sub p, because it's not just the force, it's how the force affects the oscillator, right? So depending on the forcing function that you use, is it periodic? Is it increasing over time? Is it a steady, just a constant force? Depending on what that is, but also depending on how it affects the harmonic oscillator itself, that's going to determine what your y sub p is. So the natural response, all you need to know about is the harmonic oscillator. This one's a little bit more complicated because you have to know about the harmonic oscillator, but you also have to know what's the forcing function, what's going on, what's happening external to that. So down at the bottom of this, there's a little blurb here. It says, in the long run, all solutions of a forced damped harmonic oscillator approach the steady state response because the natural response dies out. If it's a damped harmonic oscillator, it just stops mattering, right? This is why when you sit on a swing and you get going really well, and you just stop kicking your legs and hold still, you're just gonna and die out, and you'll just stop because in the absence of a forcing function, the long-term behavior of that swing is to reach or head towards equilibrium. Wah, wah. But if you're kicking your legs at just the right frequency, right? If you're just kicking your legs at just the right frequency, that can create enough of a forcing function so that that frequency of kicking your legs, that determines what happens in the long run. As long as you keep doing it, you'll keep swinging. So, handy. So this, by the way, is true for any harmonic oscillator, whether we're talking about a mass on a spring or not. So we're going to revisit our old pal, the method of the lucky guess. The fancy name for that is the method of the undetermined coefficients. But it's really just the lucky guess in disguise. And we want to find a particular solution for this non-homogeneous differential equation. Now you can tell that it's non-homogeneous because it has a term that has nothing to do with y or y prime or y double prime. That term right there is what makes it non-homogeneous. So I'm going to identify for us the part that makes it homogeneous is all this. That's the homogeneous part. And this guy right here is the non-homogeneous part. So that makes it non-homogeneous. And so if I want to solve this thing, my first step is going to be to solve the homogeneous part. And of course, we just got done saying the homogeneous part. That's the stuff that I highlighted in yellow. Solving the homogeneous part for us at this point should be pretty easy, because really what I'm doing in this case is saying, where is y double prime plus 3y prime plus 4y equal to 0? Solve that. And you're like, no problem. I just need to get the characteristic polynomial. And that looks like this. S squared plus 3s plus 4 equals 0. And you guys are, by this point in time, experts at quadratic solving. You recognize, hey, that is completely factorable. So that thing factors as what? Did you catch it? Does this thing factor? No. Yuck. But is it going to have real values for s, or is it going to be imaginary? How can you tell just by looking at it? How can you tell just by looking at it?
Because it doesn't factor.
No, that's not true.
Oh,
It could not factor and have two real values, right? That would just mean that the determinant, not determinant, the discriminant, there we go, is less than 0. In this case, b squared minus 4 times a times c. B squared is less than 4ac. So this thing is going to have imaginary values. So we don't know what they are off the top of my head. But this would allow us to get what the homogeneous part of the solution would be. That would lead us to y sub h of t equals some junk. Notice, I'm not getting in the weeds on this one because we know how to do that already. What I'm interested in is step 2. And step 2 for this one is, so once you've solved your homogeneous part, that part we already know how to do, we need to come up with a reasonable guess, a lucky guess for some y sub p particular solution. And that's the method that we're going to focus on here. So if we're going to take a look at a lucky guess for this, what we're basically saying is that the second derivative of a function plus 3 times its first derivative plus 4 times that function is equal to an exponential, e to the negative t. So what's a reasonable guess for this y sub p? Well, it's probably something like a times e to the negative t. And that should look familiar. It's kind of the same stuff that we were doing at the tail end of chapter 1 when we were doing the lucky guess back then. Now, if that's y, that would go right there. But I also need to know y prime and y double prime so that I can sub it in. So if that's y, then y prime is going to be equal to negative a e to the negative t. And y double prime is going to be, that becomes positive, so that's just a e to the negative t. So if this is a reasonable guess, a lucky guess for my solution, my particular solution, and that's its derivative and that's its second derivative, we can sub it in. We can say, if our guess is correct, if it's a particular solution, we can sub it in. And so I'm going to say, I'm going to take these 3 things and plug them in for y, y prime, and y double prime into the equation. So we'll take it out for a spin and see how it works. So y double prime is just this, a e to the minus t plus 3 times the first derivative, which is this guy right here, negative a e to the minus t, oops, minus t. And then plus 4 times the original guess, which is a e to the minus t. And that's all got to be equal to, on the other side, e to the minus t. So that has to be true. That must be true if this is a particular solution. So once we've done that, we can find the value of a that makes it true. So the thing you'll probably notice right away is that every term has an e to the minus t. And so we can kind of factor those away, and we don't have to worry about dividing them away because it can't equal 0. For any value of t, it can't equal 0. So I can kind of cross those off, and I'm left with a minus 3a plus 4a equals 1. And with a little bit of compression, you've got 4a minus 3a plus a, so that's 2a on this side, equals 1, or a equals 1/2. So what did we just found? Well, we just figured out what a particular solution of our differential equation is. We know that y equals 1/2 e to the minus t is a particular solution. Oh, my marker's starting to die again. Man, I'm killing more markers. Can't even make a basket from the side of the room. Ay, ay, ay. So we have our lucky guess. If we knew what the solution up here was, if we knew y sub h, then we'd be able to put that together with this to get our general solution, right? We're going to see some examples where we do that in a minute, but I just wanted to show you an example of how the lucky guess works, how that step 2 works. And now down at the one thing to notice is the forcing function in this case is an exponential decay, an exponential function, right? And so with an exponential function, a reasonable guess is a modified exponential function. No big surprise. But there's other things that you could select for a forcing function. Because of the reasoning on which this method is based, it works really only for a certain few type of functions, forcing functions. So it works for your constant function, or polynomial function, or exponential, as we just saw, sines and cosines, or sums and products of the above. But that's pretty much it. If your forcing function is not one of these, then this method is probably not going to work so well. And of course, there's implications for the oscillator itself. If you have an oscillator and it's being affected by a constant forcing function, that means there's a constant outside force. And so an example of a constant outside force acting on your oscillator is, well, we all live in a world in which there's a constant outside force acting on us. What's the constant outside force acting on us right now?
Gravity.
Yay! Gravity. Magnetic fields. Electric fields. I mean, these are all examples of things that could just be, that's just in the background. It's always there, right? So constant outside forces are definitely important in the solving of harmonic oscillator problems. I don't know if you remember last time when I was doing the example with the mass that was hanging from the spring, the equation that we came up with was not quite right. And the reason was there was an outside force acting on our oscillator. It was gravity, right? Constantly pulling down. So there was a constant outside force. Polynomial forces, well, the implication for an oscillator, if you have a polynomial force, it's an outside force that changes direction. Right? It has the ability to go from being a positive force to being a negative force, or from increasing to decreasing, right? So you can actually have a force that changes size and changes direction with a polynomial force. There's, tons of examples of outside forces that are stronger at one point in time and then weaker later on, right? So for example, wind. If you have a harmonic oscillator blowing in the wind, maybe the wind just kind of dies off as the day goes by. If you have a large pool of water, you're going to have different types of force acting on the oscillator, the top of the water, depending on the time of day, depending on the amount of uneven heating that's going on. So this happens. Exponential is outside force only increasing or decreasing. So unlike a polynomial, exponentials don't get to change direction. They just are always going up or always going down. And of course, they're always going up or always going down at increasingly faster rates, right? So they're only increasing or decreasing at increasing rates. Sines and cosines. What's going on if you have a sinusoidal forcing function? Well, that means you've got a force that's not just pushing in one direction, but it turns around and pulls in the opposite direction. And it goes back and forth and back and forth. And if you want to think of the perfect example of this, this is if you've ever played with a little kid on a swing, you give them a push, and then they come back and you give them a push. It's sinusoidal in the sense that it's always kind of changing direction, right? So if you're kicking your legs, you kick your legs out to go forward, back underneath you to go backwards on a swing. That's a sinusoidal forcing function. So this is an outside force that's changing direction periodically. With a magnitude or with an amplitude, right? So there's a maximum amplitude to this force and a minimum amplitude to that force. And it just goes wobbly, wobbly, wobbly back and forth. And then, of course, sums and products of the above. So you can have an exponentially decaying sinusoidal forcing function. You can have a constant that is attached to a sine or a cosine that increases the amplitude of the sine or the cosine. That works. So what is it about these particular types of functions? Why are they singled out as being the ones that we can handle? What is it? What do all of these as types of functions have in common? This is really kind of a pre-calc question. What do all those types of functions have in common? What do you think? Notice I said sines and cosines and not tangents. What does sine and cosine have that tangent does not have? Or you could think of it vice versa. What does tangent have that sines and cosines don't have?
Vertical asymptotes?
Yes. In other words, all of these functions, including sines and cosines, they're all continuous. They're all completely continuous over the real numbers. These are all continuous over the real numbers. Now, why is this important? Since we're talking about modeling harmonic oscillators and outside forces, why is it important to us that we have a continuous forcing function? What would be wrong with having a tangent as a forcing function? What would happen if you had a tangent forcing function and the input for that tangent function was getting close to pi over 2? What would happen to the tangent forcing function?
We just kind of,
It'd blow up. You'd have a forcing function that approaches infinity. And that makes no sense in reality. There's no problems with differentiation. So they're all differentiable. And the reason that these two are important is these model reality. Because in the real world, you can't have a force that blows up to infinitely large. That doesn't make any sense, right? You can't have a little kid poking a harmonic oscillator with increasingly large force to the point where it becomes infinitely large. That makes no sense. No sense. So these are the requirements of a forcing function, and these are the forcing functions for us right now that are possible. And so these are the type of functions that you're going to run into as the right-hand side of these differential equations. In this case, it was exponential, but you could just as easily run into a polynomial, t squared. You could just as easily run into a sine or a cosine, or just a number, 3, right? All of those are fair game for what we're talking about here. So let's take a look at an example. This one's going to be a harmonic oscillator, at least it could model a harmonic oscillator, with the right-hand side being that forcing function. And the forcing function in this case is an exponentially decaying forcing function. Okay, so remember what the steps are, the process, the procedure we need to follow. Step 1 is we have to solve the homogeneous part of the differential equation. Step 2 is find a particular solution. And step 3, put them together. Just like if it's a recipe and you read in the recipe, they'll say something like combine to taste, right? It's basically saying, add enough salt until you're happy with how it flavors. So really, it's just a matter of taking the two solutions, the two parts of the solution, and then scooch them together. Step 3 is the easy part, right? So let's take them in turn. Step 1, this is the chapter 3 stuff that we know how to do. Chapter 3 stuff because we're going to be solve for y sub h of t. And in order to do that, we need to solve this equation. In this case, I'm just going to write it as y double prime, but y double prime plus 6y prime plus 8y equals 0. That's what makes it the homogeneous differential equation. Oops. D, E, there we go. And in this case, it actually does work out pretty nicely. We know that this thing has a characteristic polynomial that looks like this. S squared plus 6s plus 8 equals 0. And that factors. That actually does factor nicely. S plus 4, S plus 2. Which means that there's two, you can call them if you want eigenvalues, because that's what they really are. There's two values for S. S equals -4 and S equals -2. Now, Stephen, note that those are negatives here.
thank you. I appreciate it.
So what does that mean? This leads me to the following conclusion. I have a homogeneous solution, or homogeneous part of the solution, that is K1 times e to the S1t, so they'll call this one S1 and this S2. This is e to the minus 4t plus K2 times e to the minus 2t. Look at that. Look at how easy that was. That's the homogeneous part of my differential equation solution. Now, the reason that it turned out to be so nice and easy is because they were nice and easy eigenvalues, right? There wasn't anything super fancy about them. The only time where this isn't as easy as find the eigenvalues and then shove them in this equation is if you have imaginary values, imaginary eigenvalues. And that's not that hard. You know, you're just going to wind up with sines and cosines. That's all. So that's the first part. We got that. Then it's step 2, which is we have to figure out a particular solution. And we're going to do that by applying our lucky guess method. And so we're going to say, okay, we're going to try to guess something that some y of t that when I plug it in up here, I take its second derivative, add 6 times its first derivative, plus 8 times itself, and what comes out is 2e to the negative 3t. So it's an exponential on the right-hand side. Therefore, it makes no sense to guess things like sines and cosines or polynomials, because there's no way you can take the derivatives of a polynomial and magically get an exponential out of it. The only way this is going to work is if we're going to guess something that is an exponential. And similar to what we did on the previous page, we can just guess some constant, which we don't know, times e to the, and I'm going to stick with that power, that negative 3t, because taking the derivative of an exponential doesn't change the power, right? So it's going to have to be negative 3t. The only question is, if that's what I'm going to guess, I should be able to throw it back in here for y, y prime, and y double prime. So I need to know this. I need to know that y prime is going to be equal to, so the negative 3 comes down, and y double prime, the negative 3 comes down again. It gives me positive 9a e to the minus 3t. So if I guess that, I should be able to take this thing and stuff it into my original differential equation. And so my second derivative was 9a e to the minus 3t plus 6 times my first derivative, which was negative 3a e to the minus 3t, plus 8 times the original lucky guess, which is a e to the minus 3t. And then the right-hand side, because we're dealing with the actual original equation, is 2e to the minus 3t. Now, because we guessed something that has e to the minus 3t and it's an exponential, we can just kind of like wish these away. Each one of those e to the minus 3t, those just kind of go bye-bye, and we're left with 9a minus 18a plus 8a equals 2. So tidy up the left-hand side, and you wind up with a equals what? So this is
-2.
Yeah, -2. And remember, that means that we have a particular solution, and it looks like this, -2e to the minus 3t. That is guaranteed to be a particular solution for the original differential equation. If you were to plug that turkey in to this differential equation, it would work. It is a particular solution, not the general solution, but it's a particular solution. So what can we do? Well, that's where step 3 comes in. And depending on where you were born, it's either combine or combine. That was for you, Wyatt. Putting it all together, we know the general solution is going to be my homogeneous part plus my particular part. So all I have to do is rewrite this thing as K1, let me scoot that down a little bit, K1 e to the minus 4t plus K2 e to the minus 2t plus my particular solution, which is minus 2 e to the minus 3t. And that's it. That's my general solution. Notice it's the general solution because it's got constants, but the particular part doesn't have an unknown constant. The particular part is just kind of like hanging out saying, hey, even if you let those other two constants equal 0, I'm still here. So even if K1 and K2 are both equal to 0, you still have the particular solution, which, by the way, is the textbook definition of the particular solution that we're guessing. It's what happens if the homogeneous part of the solution just wasn't there. What would the particular part of the solution still be? And this is the way we find it. There's the lucky guess method. Yay! So what do you think? Not too terribly tricky, I hope. Right? It's that follow the pattern, solve for the y sub h. We know how to do that. Find using the lucky guess method, and then combine. The tricky parts are up here for part 1. Sometimes things don't work out as nice and pretty as this. That's okay. Excuse me, that's okay. We know how to deal with those. That's 3.6, right? Sometimes the lucky guess is a little bit messy. And what do if you guess something and you find out you wind up with like 2 equals 0 or something like that, or 0 equals 0? What do you do in that case? What do you do if your lucky guess wasn't so lucky?
Guess again.
Guess again. And believe it or not, the best first step after a guess, if I guessed this and it didn't work, my next guess would be a times t times e to the negative 3t. If you guess that, it's probably going to work. And if that doesn't work, then you'd say, screw it, let's go look at Maple and see what the solution looks like. And we'll be able to figure out what our lucky guess needs to be based on what Maple says. Speaking of which, let's take a look at Maple real briefly, because I had some notes prepared in Maple. So let me go ahead and switch my share. Where the heck is it? Maple. There it is. Okay. So this is my notes from the 4.1 here. So you'll notice that, let me scooch this in because I want to be able to give it some space. We can always desolve a second order differential equation if it's equal to 0. We can also desolve it if it's non-homogeneous as well. So you can stick something other than 0 in there. You'll just get a different solution. As a matter of fact, this should look familiar. So if I change my right-hand side, by the way, notice there's my homogeneous solution. But if I stick in here 2 times e to the, negative 3 times t. If I stick that in there and say desolve, Maple says when it thinks about it, no problem. Hey, look at what it came up with. There's a constant 1 times e to the minus 2t. When I multiply that through e to the minus 2t, I get e to the minus 4t. And there's a constant 1 sitting there. So there's a constant. The last term is going to be c2 times e to the minus 2t. And the middle term is going to be that particular solution, negative 2 e to the minus 3t. It works. So our method gets us the solution, an analytic method for finding the solution that Maple backs up. I will note that there's something weird going on there with a extra constant. sitting in there. There's like a -1/2 sitting there. And the reason that it's there is because the method that Maple uses to find that general solution is actually what we would recognize as the the other method that everybody loves from chapter 1, the integrating factor method. Yeah. So Maple actually uses the integrating factor method, and I actually have a little worksheet, a Maple worksheet that explains how that solution comes to be, and I'm going to post that so you guys can take a look at that later on. But this works out. This really is the same solution as what we found. So Maple's capable of doing that. The other thing I want to make sure everybody's clear about is Maple can also do a DE plot of a second order differential equation. We just have to add some initial conditions. If you just tried to get Maple to do a DE plot of this thing, the equation itself, Maple would freak out. It wouldn't know what to do. But if you add initial conditions, it will give you the output is a graph. It's basically the graph of the solution, y of t. Right? And so if I wanted to, I have to make sure I hit this. If I wanted to, I could throw that same 2 times e to the -3t. I could throw that in there, and you'll see what happens. Our new solution looks like this. You're like, wow, that's pretty much the same thing, isn't it? Well, not quite. Before we had something that had a 0, and it reached a height a little over 0.12, and then it kind of died out by the time t got to about 5. But if instead we had this 2e to the -3t, it goes a little bit higher initially, but then dies out again. Because this thing is responding to that forcing function, but the forcing function is exponentially decaying with time. So by the time you get out here, the forcing function is practically 0. So for us, it doesn't look like there's much going on. What if I changed and made it, instead of an exponentially decaying forcing function, what if I made it a constant forcing function? What if it was just equal to 2? We get this. Looks very different. But what do you see happening? Well, there's that initial uptick, but then it just kind of like hovers up here. The long-term behavior of this harmonic oscillator is determined entirely by that forcing function. There's a constant force acting on it, and so over time, it just kind of like reaches a new approaches a new equilibrium. If you say, well, what if it's a forcing function like this? What if it's 2 times the cosine of t? What do you think it's going to look like? In your head, try to imagine what you think it's going to look like. In the long term, that cosine function is going to win. The harmonic oscillator dies out. The natural response dies out, and you're left with basically a cosine curve. It didn't initially start off that way. Notice it goes up a little bit higher than these other ones, and then it kind of falls into line, and it becomes just a cosine function. Right? Wobble, 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 wobble. The long-term behavior of our harmonic oscillator follows that forcing function. So if it's a cosine function, the long-term behavior is going to be sinusoidal. It's going to be a cosine as well. So switching back over, we're going to do one more example in the notes. I don't know if we'll get to all of them, but we'll do one more example in the notes here. So let me switch back to this. And let's take a look at an example. Actually, I'm going to skip this one because, well, is that one that I want to do? No, let's do this one because this one's kind of interesting. Is this one kind of interesting? No, that one's not really that interesting. I'm going to skip this one. I'll have you guys finish it. It'll be in the video that I post, but skip it for, well, do I want to skip that one? Yeah, no, let's do it. Let's do it because something interesting happens with this. Sorry, I'm deciding on the fly. So what happens with this? Well, let's see. Remember the rules. What are we aiming to do? The first part is to solve that y sub h. The second step is to find the particular solution. And then the third step is to international harvester. My country folk get that joke. Okay. It's not that funny. Okay. So first step is I got to find that y sub h, which really means I'm going to be solving this equation, y double prime plus 5y prime plus 6y equals 0. This gives us a characteristic polynomial of s squared plus 5s plus 6 equals 0. And that thing does factor. It factors as s plus 3 times s plus 2. And so we have two possible eigenvalues, which are -3 and -2. So pretty boring. This leads us to a homogeneous part of the solution, which is just k1 e to the minus 3t plus k2 e to the minus 2t. So step one, not particularly tricky because go figure, it's pretty easy to factor that polynomial. Step two, that's where we're going to find our y sub b, and that involves a little bit of lucky guessing. And so what would be a reasonable lucky guess if that's our second order differential equation? What would it be? What would you guess?
e to the negative 2t.
Sure. A times e to the negative 2t.
I feel like we should add a t in there.
Ooh,
Like t
why
times a.
why do you feel that way?
Because you mentioned it last time, and then you said this is a little bit tricky. So just
Yeah, you're like, well, wait a minute. If part one wasn't tricky, then it's got to be part two. Yeah, this is the part where you're like, everybody stop. We need to check for traps. There's got to be something going on here, right? So you're right. We're going to wind up. But I want you to see how it looks. What does it look like when we run into that? So that's our y. Y prime is just going to be negative 2a e to the minus 2t. And y double prime is going to be 4a e to the minus 2t. And if you're playing the at-home game, you can probably see this coming a mile away. When I do the substitution, when I sub that thing in, we're going to wind up with my second derivative, 4a e to the minus 2t, plus 5 times my first derivative, which is negative 2a e to the minus 2t, plus 6 times my original guess, which is a e to the minus 2t, equals e to the minus 2t. So again, like we did before, we've got this e to the minus 2t. That kind of works out nice whenever you have the exponential guess, because those all just cancel away and you're left with 1, which means that we have 4a minus 10a plus 6a equals 1, which of course can't possibly happen because this side is 0. Zero equals 1 is impossible. It's not even like Kim possible. This is totally, completely impossible. And so if you ever run into a situation where substituting a value into an equation tells you something impossible, like 0 equals 1, then the only logical conclusion is whatever you put in to that equation is not a solution. It doesn't work. So that means y equals a e to the minus 2t is not, it's never a solution. So what do you do when you have a bad lucky guess? You guess again. And so that's what we're going to do. We're going to say, well, if that guess didn't work, Let's try another one. And this is where Stephen is right on the money. We're going to guess a times t times e to the minus 2t. Now, the only thing about this that makes it a little tricky is that's a product rule situation. When we're going to take his derivative, that's a product rule. So if that's y, then y prime is going to have two terms instead of one. The first term is when we're taking the derivative with respect to t, and I focus on the first factor, right? So it's just going to be the first term is going to be a e to the minus 2t. The second term is going to be a times t times this thing's derivative. So it's going to be minus 2a t e to the minus 2t. And then, of course, we can do the same thing for y double prime. And because y double prime is taking the derivative of this, it's going to have a term from this thing's derivative and then two terms from this thing's derivative. So it's just clunky. It's just a little bit more calculus. It's not terrible. It's going to be negative 2a e to the minus 2t. I'm not going to be able to fit it all in on this line here, but I'll squeeze, or I'll write it underneath here. The next term is going to be minus 2a e to the minus 2t. And then I'm going to have the derivative of this thing where I negative 2at times the derivative of that, which is going to give me plus 4at times e to the minus 2t. So if you're thinking, oh my God, this is getting really complicated, it's not too bad. Because just like we did before, we're going to substitute these three things in and see what we get. Now, these three things, notice that we have, in this case, negative 2a e to the minus 2t minus 2a e to the minus 2t. So that simplifies a little bit. So it's just going to be minus 4a e to the minus 2t plus 4at e to the minus 2t plus 5 times its first derivative, which has got two terms as well, a e to the minus 2t minus 2at e to the minus 2t plus 6 times the original guess, which is a t e to the minus 2t. And all of that on the other side equals just e to the minus 2t. Now you'll notice there is no term on this side that is t times e to the minus 2t. So hopefully it works out. And if you look at the side, you can see what happens. All of our e to the minus 2t, those things cancel out. Those terms, or excuse me, those factors cancel out. And you're left with minus 4a plus 4at plus 5a minus 10at plus 6at equals 1. So by adding that additional factor of t, all that we've really done is kind of kicked that cancellation situation down the road to the terms with the a times t. So 6at minus 10at plus 4at, those all go away. Those sum together to equal 0. And all I'm left with now is a little bit more manageable, a equals 1. So it worked only because that first guess was a complete and utter failure, right? We were able to figure it out because that first guess was wrong. So this is what it looks like when you have a guess go bad. You wind up with something impossible and you go, that can't be. Let me try another guess. And usually a good guess is multiply by t. Multiply your guess by t and try it again. That's usually a pretty good shot. By the way, we're not done. We know our particular solution for this is now 1 times t times e to the minus 2t. So that's my particular solution, which means that we're ready for the last step where we combine. And this is going to give us our general solution, which is my homogeneous part, which is way up there, K1 e to the minus 3t plus K2 e to the minus 2t plus t e to the minus 2t. So this is another example of how it all works out. But the same three-act structure holds. Figure out your homogeneous solution, figure out your particular solution, and combine them together. So this last one, because it's essentially the same left-hand side, but with a constant forcing function, I'm going to leave this one for you guys to finish. And the only other extra is I give you some initial conditions that you can use to find the particular solution. And then at the end, it says find the exact value of y of 2. So once you're done, you're going to plug it in and find out. So this one actually has part 1 is solve for y sub h. Step 2 is find your y sub p. Step 3 is to combine to get y of t. Step 4 is to find the particular solution, so solve the initial value problem. And then step 5 in this one is going to be predict y of 2. Oops, sorry. So that actually has 2 extra parts to it, but they're just extra parts that are, okay, now that you've got your general solution, what's the particular for those initial conditions? What's the initial value problem solution? So what I'd like us to do right now, we only have like 10 minutes, a little over 10 minutes, but that's going to be enough time for us to be able to hop into groups. And you'll notice it doesn't really matter what group you're in because everybody's working on the same problems. What I'd like for you to do for the classwork problems is to take a stab at solving number 1 and number 3. So start with number 1 and see if you can collectively come up with it. What I'd like you to do is have one person be the Maple jockey, hop in there, solve it in Maple while the other people are doing the handwritten part, and so you can compare notes. Does that make sense? Quentin's like, oh, sorry, I was catching up on some YouTube. What were we watching? I'm going to have you guys do these solutions for number 1, and you'll see number 1 on the classwork is basically just find the general solution. So it's step 1, step 2, step 3. So give that a go. I'm going to put you in the breakout rooms, same breakout rooms as before. Go, I'll be around if you need anything. If you finish up with that one, give number 3 a try. And I will pause because there's no point in continuing.